All right, good morning, everyone. So today we're going to be talking about the fine structure constant of the hydrogen atom. So let's just do a little bit of review of the hydrogen atom bound states. Okay, and so they all have negative energy. And so if I graph, here's my zero of energy right here. And if I sort of graph where the hydrogen atom bound states are, there's the ground state, which is down here somewhere. And we'll say that's -1 Rydberg, which is minus 13.6 electron volts. And that state necessarily has angular momentum 0 when we solve for it. And that's the n=1 state. So by the way, for different problems, you have to keep track of which is the principal quantum number n. So for example, in some problems like the harmonic oscillator, the ground state is n=0. For the hydrogen atom, it happens to be n=1. These are just labels. So one can't assign absolute significance to them, but that's the convention. And the n=1 is something that goes into the energy expression. So up here at 1/4 of that, pretend that's a quarter, is the n=2 state, or the n=2 level, at -1/4 Rydbergs.
Professor,
And there's that one, and there's the L=1. Sorry, did you have a question?
yes. Is there a reason why those are shorter than the E=0?
You mean the lines?
Yeah.
Oh, no. It's just I'm a lousy artist, that's all. Okay? So the n=2 state can have L=0 or L=1. And then up here, there's -1/9 Rydberg. That's the n=3 level. And that can have L=0, L=1, or L=2. And then there's -1/16 Rydberg up here. And that can have up to L=3. Okay, and so there's this sort of amazing accidental degeneracy between different levels of L. It's not true for just a generic Hamiltonian that states with different L are going to be degenerate. It's a very special property of the hydrogen atom, but it's nevertheless true that you can look at the degeneracy of level n. Okay, and so what is that? First of all, there's a factor of 2 because the electron has spin, which we will be taking into account. And then for a given n, I can sum over all the L's that contribute, which is 0 up to n-1. And for each one of those, there are 2L+1 different values of m. And when you do that sum turns out to be n². And so the total degeneracy is for each level is 2n², except even that isn't right because there's also proton spin, which we're not going to talk about for a while, but we will come back to it. So proton spin gives another factor of 2, which will be important later. Okay, now the fine structure is just the fact that all of this was assuming or not taking into account special relativity. And when you do take into account special relativity, the fine structure splits apart these otherwise degenerate states, and so they're not quite degenerate. So this is relativistic effects. That split the degeneracies. They don't completely split the degeneracies, as we will see, but we'll want to understand to what extent some of these degeneracies are split and some of them remain. Okay, now we're going to be consumers of the relativistic effects. We're not going to actually derive them. So I'm just going to tell you that from the Dirac equation, which is special relativity applied to quantum mechanics, that adds some terms to the Hamiltonian of the non-relativistic thing. And we can write everything, let's write everything for future reference in terms of a general electrostatic potential, which is the charge on the proton divided by the radial coordinate. So that's our potential. I'm going to write it in terms of a general potential because later we will apply the equations that I'm about to write down to a more general case, rather than just a proton.
Sorry to interrupt you. I just couldn't read that word in that last sentence.
This says from Dirac equation, relativistic quantum mechanics. Is that what you mean?
No, the one before the last sentence.
So that says fine structure equals relativistic effects that split. Oh, that's misspelled. Degeneracies.
Thank you.
Pretend that says degeneracies. There we go. Okay, so what does the Dirac equation tell us? It says the whole Hamiltonian has the following parts to it. First of all, there's a constant part that we can just ignore, but it's nice to know it's there. And that's just Einstein's energy equals mc squared. But because it's a constant, it just shifts everything by the same exact amount. It does the same, when you do time evolution, it puts the same complex phase in front of every single state, and therefore it's not observable. Okay, and then there's the piece that we actually used when we solved the hydrogen atom, which is this part. Okay, and so this is going to be, for what we're going to be doing for the next few days, that's going to be our unperturbed Hamiltonian, and we already know its exact eigenvalues and eigenstates. And now there are the corrections to it. So the first correction is the momentum squared squared. Momentum is a vector, that's why I'm writing it as momentum squared squared, divided by 8 mass of the electron cubed, it turns out, speed of light squared. Then there's another term which I can write like this. It's minus the charge on the proton over twice the mass of the electron squared, speed of light squared again, 1 over radial coordinate derivative of the potential, which of course we could just do that derivative, but we're trying to be general, as I mentioned. And this is multiplied by the orbital angular momentum dotted into the spin. And then there's finally this term, h bar squared charge over 8 me squared c squared, and now the Laplacian of the potential. Okay, so you're just supposed to believe me that this is what comes out of the Dirac equation. I'll give some, in a minute, I'm going to give some very hand-waving explanations of what sort of things give rise to these. This first one is sometimes called the relativistic or relativistic kinetic term. The second term is called the spin orbit correction. And it's either written as HSO or HLS, depending on whether you want to say it's spin orbit because it involves the orbital angular momentum and the spin. Okay, and then the last term is called the Darwin term. Okay, and together, these make up the fine structure Hamiltonian for the hydrogen atom. Okay, and notice that they're all of the same order. Okay, and in particular, they all have a 1 over speed of light squared in them, which is a signal that you're talking about something that's a relativistic effect. In fact, if you were to somehow take the speed of light to infinity, all of these terms would just go away and we wouldn't have to worry about them. So the only reason that we need to include them is the fact that the speed of light is finite. Okay, so we will treat this, actually we'll treat them each separately as perturbations, because the fact that the speed of light is very large means that they are going to be small. Okay, and for each one of them, we're going to find the energy shifts using perturbation theory. But we're not even going to worry about, at least in this class, we're not going to worry about the effect on the wave functions, although we could. But we're mostly interested in energy levels. Okay, so let me say a few words about the origins of these terms sort of physically. You can just do the Dirac equation and just sort of turn the crank mechanically and out they come, but it's useful to think about where they come from more heuristically. So the relativistic correction comes from, it's the most straightforward thing. It just comes from the fact that in special relativity, the energy is equal to the speed of light times the momentum squared, which I'm going to write classically as a small p, plus m, the mass squared times the speed of light squared. And so all we do is we expand that for small p. So I first extract a factor of the mass and the speed of light. And then I'm writing this as 1 plus a small number, which is momentum squared over mass of the electron squared c squared. That's not very clear. Let me rewrite that. So this is mass of the electron squared c squared, and this is to the 1/2 power. And then you do a Taylor series expansion of that. The first term is just 1, of course. The second term is p squared over twice me squared c squared. And the third term is, oops, it's minus 1/8 p squared squared over me squared c squared squared. Okay, and then if you just plug that in, multiply it by that. So the first term is actually giving us the constant. The second term is giving us the kinetic term that we know and love. And this is giving us the relativistic kinematic correction. Okay, and this really continues on. So if we wanted to, we could worry about the p to the 6th term, but that would be really, really small. And so we're going to neglect that. Okay, so that was the relativistic correction. And now for the spin orbit. And here we're going to be a little bit more hand wavy. So the spin orbit Hamiltonian is basically coming about from the fact that the spin of the electron is going to be interacting with the magnetic field that it sees. So it comes from a correction to the energy, which is minus the magnetic moment of the electron dotted into the magnetic field, which is the effective magnetic field that it sees as it moves. Okay, so B effective is equal to the magnetic field in the electron's rest frame. Okay, which is equal to minus 1 over the speed of light squared, the velocity of the electron cross into the electric field. So what we're going to want to do is we're going to want to interpret that velocity in terms of the operator momentum. So that's the first thing we need to do with this. We're going to say the velocity of the electron is its momentum divided by its mass. And then we promote the momentum to an operator. And the other thing we're going to do is we're going to say the electric field is minus the gradient, minus the gradient of the potential, of the electric potential. Okay, and now we're going to use, we're still going to try to be as general as we can, but we're going to assume the potential doesn't depend on angles, it only depends on the radial coordinate. So assume phi only depends on the radial coordinate. So it doesn't depend on theta and phi. And the advantage of doing that is then we can take the gradient as just derivatives with respect to the radial coordinate. So the electric field is minus r hat times the r derivative, which I can write as minus r the vector divided by its magnitude times the derivative. Okay, and so all of this is, now we can promote the r into the position coordinate. And so we've got our effective magnetic field that the electron is seeing is equal to the momentum operator crossed into the position operator divided by the mass of the electron times c squared times 1 over r, the derivative of the potential function with respect to r. And the nice thing about this is P cross r is otherwise known as the orbital angular momentum. That's how it's coming into this. And so this is orbital angular momentum divided by mass times c squared, 1 over r d phi by dr. Okay, so we've sort of done half of this. We've done this part. And now we need to think about the magnetic moment of the electron. Oops. So the magnetic moment of the electron is proportional to the spin. Okay, and in fact, it's the charge divided by the mass times the spin. All right, so now we can put that together and we see where our L dot S is going to come from. But it turns out this has been a little bit too naive. So I'm going to write naively here. The Hamiltonian would be minus E over ME squared, C squared, 1 over R d phi by dr. And then there's the L dot S. So the reason I say naively is it's got all the right factors, almost. The only problem is that if you actually do the Dirac equation and work it all out, you get a factor that is exactly half of that. And that extra factor of half caused a lot of confusion historically. And it comes from, or it's called the Thomas precession effect. Basically, the argument we've just given says it has to be of the same order of magnitude that we just derived. But the Thomas precession effect comes about because the naive thing that we did is that we treated the electron as if it were in an inertial frame, meaning it's not accelerating, but actually it's in a rotating frame, which means it is accelerating. So electron is in a rotating frame, which is not inertial. Okay, and so there's that accounts for why there's actually an extra factor of 2 in the denominator right here. And so that is what I wrote up here. Okay, and then the third one we're going to be even more hand-wavy about. Okay, so the Darwin Hamiltonian comes about from the fact that the electron can't be localized better than its Compton wavelength without producing electron-positron pairs. And so that sort of modifies the potential at very short distances. So better than its Compton wavelength. Okay, the Compton wavelength, or the reduced Compton wavelength, is a is a number of units of length that you can form out of h bar and the mass of the electron and the speed of light, like that. Okay, and so at very short distances, the potential gets modified. And the way it gets modified turns out to be that it gets replaced by itself minus this Compton wavelength squared divided by 8, it turns out, times the Laplacian of the potential. Okay, so there's no way, of course, from just me hand waving about Compton wavelengths and how electron-positron pairs get created out of nothing, that I could tell you why it's 1/8. Again, one gets this from the Dirac equation. Okay, and so again, I'll emphasize that all three of these effects are relativistic in origin. The kinematic effect was the most obvious ones, but the other are also relativistic effects. Okay, and they go to 0 as the speed of light goes to infinity. All right, so now we're just going to be treating these as perturbations. We're going to work at first order in perturbation theory, which means that we're just going to be computing expectation values of these three Hamiltonians in the various states, and just adding those to the energy eigenvalues. Okay, so first, let's do the relativistic one, which is not necessarily the easiest one. So the first order correction to a hydrogen atom state labeled by the usual quantum numbers NLM is going to be the expectation value in that state of minus p squared squared over 8 mass of the electron cubed, speed of light squared. Okay, so all we have to do is compute that expectation value. And now the wrong thing to do is to write this in position space and try to do integrals over Laguerre polynomials and things like that. You can do it that way. It's just not the most efficient way. And so just like when you're doing a harmonic oscillator problem, the last thing you want to try, if everything else fails, is to use Hermite polynomials, because they're a big mess. In the same way, the last thing we want to do here, especially if it's a general thing here where we're not specifying what N, L, and M are, the last thing we would want to do is write things in terms of the actual position space wave functions. So instead, we're going to use tricks. And so how are we going to use tricks? The first thing we're going to do is notice that we're computing expectation values of p squared squared, and p squared over twice the mass we can rewrite as the unperturbed Hamiltonian plus e squared over r. So the reason that's an advantage is because we know what the unperturbed Hamiltonian is acting on these states, NLM. And so we can just replace it by its value. So ENLM, first order correction, is NLM. Okay, and now I'm just going to write minus 1 over 2 MEC squared. That's the stray factors that aren't being included here, times H0 plus E squared over R all squared. Okay, and then I replace H0 by E sub n. Remember, the unperturbed energy doesn't depend on L or M. Okay, and so the term with just H0 squared is just the unperturbed, let me write it as curly E, the unperturbed energy squared. And then there's a term with 2 times the H0, which again is the curly E, times E squared. times the expectation value of 1 over r. Okay, and then the last thing is e to the 4th times the expectation value of 1 over r squared. Okay, so instead of doing expectation values of p squared, which is horrible because if you were to try to do that, you would be taking a Laplacian squared, you'd be doing a lot of derivatives, acting on a bunch of Laguerre polynomials. Instead of that, we've isolated into expectation values of powers of the position operator. So for homework, you're going to get to do some general tabulation of different expectation values of powers of R for the hydrogen atom. And I know you can look these things up. That's not the point. The point of the problem that you're going to be doing for homework is to learn how to do them in general using recursion relations. Here I'm going to be doing that partly, but I'm going to be doing some alternative tricks. Okay, so this is going to be, the first trick is going to be an alternative to what you're doing on the homework. Let me do this. Let me say this is for the expectation value of 1 over r in the state NLM. Okay, and so here's the trick is we're going to consider temporarily another problem. We're going to consider a Hamiltonian that depends on z, the charge on the nucleus. So we're going to write it as p squared over 2me minus z, e squared over r. And what we're going to do is we're going to write that as, so we're going to write hz equals the hydrogen atom h0 plus a perturbation w that we're going to treat as small, where h0 is the usual thing, and now w is going to be 1 minus z e squared over r. So in real life, z is always an integer. So this is either 0 or it's not a small perturbation, but there's nothing preventing us from living in a dream world where z can be anything. And so we could imagine z is very close to 1, and then that's a small number like our lambda in perturbation theory, and we can go ahead and trust perturbation theory. So now we're going to do two things. We're going to remember what the exact eigenvalues are. So from, for example, physics 660, the exact energies are the following. You just have to remember where to put the powers of z. And it turns out they look like this, minus me e to the 4th over 2 h bar squared n squared. There are two powers of z, it turns out. But now what we're going to do is, because we want to compare this to what we would get from perturbation theory, we're going to rewrite that as 1 plus z minus 1 all squared. I've just rewritten it. And now I'm going to expand in small z minus 1. So this is minus me c to the 4th over 2 h bar squared n squared. And there's the first term is 1, and the second term is 2z minus 1. And then, of course, the expansion just has one more term in it, but that's not the point of this. The point of this is just to isolate the contribution that goes like z minus 1. Okay, and the reason that's the point is now we're going to compare to the fact that in perturbation theory, the first order correction is just that thing proportional to z minus 1, namely me c to the 4th over h bar squared n squared. The 2's cancel, and the minus signs cancel if I write this like 1 minus z. that must equal, okay, the expectation value of 1 minus z e squared over r.
I'm sorry, Professor, I don't want to interrupt you.
Uh-huh.
In that line where you wrote, right under where you wrote from physics 660, and
Yeah.
then you e, is that e to the fourth or c to the fourth?
Oh, sorry, that's, wait, oh, that's e to the fourth. I should be writing e to the fourth here.
Okay, thank you.
Can't even read my own writing. There we go. Okay, so now, so this was just the perturbation. This is what we got by expanding out the exact answer and isolating the term in both cases proportional to 1 minus z. And so the two things must equal each other. Notice this is just proportional to what we want, the expectation value of 1 over r. And so what we get when we isolate that is the expectation value of 1 over r is me e squared over h bar squared n squared. Okay, and that's equal to 1 over the Bohr radius times, it turns out, n squared. So just the fact that we're computing an expectation value of 1 over a radial coordinate means the answer has to have units of 1 over distance. And really the only distance is, in this situation, is the Bohr radius, because the speed of light isn't coming in, so the Compton wavelength can't come into the problem. Okay, so it had to be 1 over the Bohr radius times something, and the something just so happens to be 1 over n squared, where n is the principal quantum number. Okay, so that was what we needed for this one. And now we need the 1 over r squared, for which we're just going to use another trick. By the way, for the homework, I do not want to see you just reproducing this. I want you to see the method used in that problem, specified in the problem. So the another trick is going to be used for 1 over r squared. In the homework, you're supposed to use the answer that I'm about to derive for 1 over r squared, because the trick in the homework, this is the one case that the trick in the homework won't work for. So again, what we're going to do is we're just going to invent our own dream world Hamiltonian. And our dream world Hamiltonian is going to be the usual one. But now we're going to add to it a different perturbation, which is going to be proportional to 1 over r squared. Why? Because we want to find out something about the expectation value of 1 over r squared. And so this is going to be our H0, as usual. We're leveraging the fact we know its exact eigenvalues, and that's our perturbation. And so for this particular Hamiltonian, we are interested in the first order correction to the energies. And so, as usual in perturbation theory, that's just the expectation value, lambda times 1 over r squared. That's the thing we want. And so if we can compute that correction some other way, then we will have the answer that we need. Okay, so we need some other way to calculate that energy correction. So I'll write meanwhile. So here's where we're actually going to write down the differential equation for the Hamiltonian. For the exact version of this Hamiltonian, which looks like this. Don't worry, we're not actually going to solve this differential equation. We're just going to leverage again what we already know. Okay, that acting on the wave function in position space has to equal the exact energy eigenvalues for our H lambda Hamiltonian acting on the wave function. Okay, now how are we going to leverage what we already know? That we do by noticing that this Hamiltonian already had a term proportional to 1 over r squared. And so if we want to, we can absorb this term that we added into that term. And that will just change what L is. Okay, so mathematically, what we're saying here is, let's let h bar squared over twice the mass of the electron times L plus 1 plus lambda, right? So we're combining these two terms. Let's call that equal to h bar squared over twice the mass of the electron L prime times L prime plus 1. Okay, so this defines what L prime is. L prime is defined in terms of L and lambda. And if I really wanted to, I could solve a quadratic equation to be more precise, but actually we won't need to. Okay, so now what we notice is because we've done that, we know what the exact energy eigenvalues for lambda are. They're the same thing as the usual hydrogen atom when we solve that differential equation. And remember, there was this integer k, which was k plus L was equal to n. So I'm going to write that integer here, k. But now instead of L, it's L prime. And it went like 1 over n squared. So it looks like that. So those are the energy eigenvalues where k, again, is an integer that's non-negative. Okay, so now we just notice that we can expand that in small lambda. E of lambda is equal to what we would have gotten when lambda is 0. That's when L equals L prime. Plus, when you do a Taylor series expansion, it looks like this. Lambda times the first derivative, evaluated at lambda equals 0. Plus dot, dot, dot. We could, if we wanted, do lambda squared, but all we want is the first term in the expansion. That second term here must be, or it must equal, the first order correction to the energy, right? Which we know from above is lambda times the expectation value of 1 over r squared, which is the thing we want. Okay, so now we've reduced it to, can we evaluate this thing? And of course we can, or I wouldn't be showing you this trick. Okay, so what we've learned is the expectation value we want is d by d lambda of minus m e to the 4th over 2 h bar squared k plus L prime plus 1 squared. Okay, and then we're going to, after we do the derivative, we're going to plug in lambda equals 0. Not before we take the derivative. So now we take the derivative, we get m e to the 4th over 2 h bar squared k plus L prime plus 1 cubed. There's a minus 2 from the fact that there was a negative 2 exponent. And we're using the chain rule here. So there is also a dl prime by d lambda. Okay, and then at the end, we're supposed to plug in lambda equals 0. Okay, so now we need to evaluate dl prime by d lambda. Okay, but that we can do by going up to this defining relation and taking differentials of everything in it. Well, basically lambda is changing, so we're going to take a differential of lambda, and we're going to take a differential of L prime. Okay, and so from that, we get h bar squared over 2me dl prime by d lambda. That's what we want, times do L prime plus 1. Okay, and that is equal to h bar squared over 2me d by d lambda of L times L plus 1 plus 1. That's from going back up here. That's from this term. And the first term on that side is equal to this. That's this term. Okay. So the thing about that first term is it's 0 because L didn't depend on lambda. It was L prime that depended on lambda. So that's 0. And so what we get is that dl prime by d lambda, when I plug in lambda equals 0, is going to be 2me over h bar squared 2l plus 1. All right, so now we're finally ready to just put all that together. And so what we get is the expectation value of 1 over r squared in the state NLM is 2me squared e to the 4th over h bar to the 4th n cubed 2l plus 1. And now the thing is, this must be proportional to 1 over the Bohr radius squared. And the question is, what's multiplying it? And the answer is just everything in there that depends on n and l. So this turns out to be 1 over the Bohr radius squared times n cubed l plus 1/2. Okay, so that's the end of the tricks, at least for today. We've computed the 2 matrix elements that we needed. And now we're ready to plug them in. Let's go way back and look at what we're supposed to plug them into. That was all tricks, tricks, tricks. Okay, and now we're supposed to plug them into this equation. And we know what the unperturbed energies are to plug into that equation. So we've now got everything we need to plug in there. Okay, and so from the H relativistic perturbation, next time we're going to have to do the other 2 perturbations. So we've only done one of them. We've got ENLM. I'm going to write first order in perturbation theory, and then relativistic. This is minus 1 over 2 mass c squared. And then there's minus e squared over 2 Bohr radius, that's the Rydberg, times n squared, squared. Okay, that was curly en squared. Plus 2. I'm going to write my curly e again. But that was multiplied by e squared, and then 1 over Bohr radius n squared. Okay, so that was curly e. That was my expectation value of 1 over r. And then finally, there's e to the 4th times 1 over Bohr radius squared n cubed l plus 1/2. Okay, that was the matrix element of 1 over r squared that we computed. All right, so now we notice that all of these look very similar, and we can combine them by writing minus e to the 4th 2 mass of the electron. There's a Bohr radius squared in each term. There's a c squared in the denominator, multiplying the whole thing. And then there's 1 over 4 n to the fourth minus 1 over n to the fourth plus 1 over n cubed times L plus 1/2 from the three terms. And now we can extract out a factor of 1 over n cubed and a minus sign. And so this turns into e to the fourth 2me Bohr radius squared c squared 1 over n cubed times a combination 3 over 4n minus 1 over L plus 1/2. Okay, so that's simplified nicely. And we can rewrite this first term, this first factor, I should say, as, well, so a clue as to how we should rewrite it is the fact that we're computing an energy correction here. And the energy correction, the energy associated with this problem is a Rydberg. So let's extract a factor of a Rydberg. This is e squared over twice the Bohr radius, that's the Rydberg. And then what's left over is e squared over mass of the electron. There's the stray factor of the Bohr radius times c squared. Okay, and then I guess when I write equals sign, I shouldn't put that because really what I'm doing here is I'm just working on this prefactor. Okay, and so another way of rewriting that prefactor is when we take the Rydberg part, we want to get rid of the Bohr radius in the other part, which we can do by plugging in what it is, and we get e to the fourth over h bar squared c squared. And that turns out to be the fine structure constant squared, which is why this is why the fine structure constant is called what it is. So that's what we've called alpha squared. It's a dimensionless number. And then the other part is the Rydberg. So numerically, this is 13.6 electron volts. And the alpha squared, the fine structure squared, is 1 over 137.036 something squared. So all of this is telling us that we really are on the right track in treating this as a perturbation, because this is indeed a very small number times the binding energy. Not only is it a very small number, but for anything other than n equals 1, this is going to be a even smaller number, at most 1/8. And then these numbers are going to make it even smaller. So there's nothing here that's going to make perturbation theory go bad. And in fact, perturbation theory works perfectly well. And so we can rewrite the whole thing as fine structure constant squared Rydberg 1 over n cubed, and then this funny factor 3 over 4n minus 1 over L plus 1/2. Okay, so some things to notice about this is, first of all, this depends on n, of course, but it also depends on L, which is a signal that this thing is trying to break the degeneracy associated with, that we started off with, where different n levels can have L's that are giving you the exact same energy. This thing is trying to split them apart. Okay, now you can't take this too seriously at this point though, because there are other terms that have the same parametric form. They're going to turn out, the other two terms that we're going to talk about are going to have the same prefactor here. but they're going to have a different dependence on N and L. And so this by itself is actually kind of useless. We have to compute those other things, add them all together, which are all going to be of the same rough order. And only then will we be able to conclude that the degeneracy is indeed broken. And it will be broken in a slightly different way than what we see here when we do those other terms. Okay, so next time, we will do the spin orbit part. And then for homework, you will get to do the Darwin term, which is good because the Darwin term turns out to be the easiest one. So that's why you get to do it for homework. And then when we get all three, we'll add them all together and we will have the complete fine structure of the hydrogen atom. All right, any questions on today's lecture? All right, so if not, don't forget that there is a new homework set out, which is due a week from last night. And I'll see you all on Monday.
Thank you so much.
Professor?
Mm-hmm.
I have a few questions.